For Objective 3, we're going to learn how to clear multiplication and division from an expression or an equation. And because I had numbered the first set of rules wrong, these are going to be backwards. So now we're looking at Part 6. Can we get rid of the things that are being multiplied or divided by our variable? So if I look at this first expression, it looks like it's almost solved because it's got a t equaling 4. But that negative sign in front of it makes things different. It means that there is still something getting multiplied by t, that there's a -1 getting multiplied by t. So in order to get rid of that -1, I would need to divide by -1, or multiply by the inverse of -1, which is still -1/1. So if I divide the left side by a -1, I need to do the same thing on the right side. And that's going to leave me with t equals -4. Checking that answer, I'm going to put a -4 in place of my t, and I end up with the original negative that was on the outside, then the negative that comes with my answer that needs to equal 4. And since minus a -4 does convert to a +4, this answer checks out. In this next problem, I have my variable getting divided by a 4. Well, the way that I can get rid of a divided 4 is by multiplying by 4. Multiplying by 4 will get the 4's to go away and leave me with just a d on the right side. But the golden rule says if I do something to one side of my equation, I need to do the same thing on the other side. So I'm also going to multiply the right side of the equation by 4. And that's going to give me a -36 on the right side. Then I'm going to check my answer. I'm going to put the -36 in place of the d. -36, when I divide it by 4, should equal -9 if I've done my math right. So we'll check it. 4 divided into 36 is a 9, and a negative divided by a positive is a negative. So sure enough, this checks out. The answer is correct. In this last example, I have c being multiplied by 50. So to get rid of that 50, since it's being multiplied by c, I'm going to divide by 50 in order to get the c alone. But if I divide by 50 on the right, I also have to divide by 50 on the left, which leaves me with a -75/50ths equaling c. I can then reduce my fraction. Since both 75 and 50 are divisible by 25, my final answer is going to be a -3/2 is equal to c. When I go to check this, I put -3/2 in where my c used to be. I have a -75 on the left, and then a 50 times -3/2 on the right. I can turn this into a fraction by putting a 1 under it, reduce my fraction by dividing both of those numbers by 2. That'll leave me with only 1's on the bottom, and a 25 times -3 on the top. 25 times -3 is -75, and that's exactly the answer I was looking for. So yes, that answer checks out. In this next problem, the directions say we're going to solve equations of the form ax plus b equals c, which is kind of an awkward way of saying you're going to need to be able to clear multiplication from your variable, multiplication or division, and you're also going to need to be able to clear addition and subtraction away from your variable. So it's going to take, back to our steps list, clearing both of these kinds of operations and then still checking our answers to make sure that they're correct. So let's try a couple of examples. We always want to clear the subtraction and addition before we try to clear the multiplication. So my first step with this problem is going to be to add 1 to both sides of my equation. That will give me 6 u's left on the left and an 18 on the right. Then I'm going to clear the 6. Since it's getting multiplied by u, I can get rid of it by dividing. When I do the same thing over here, I end up with u equals 3. To check this work, I'm going to substitute the 3 in place of the u. So I get the equation 6 times 3 minus 1 is supposed to equal 17. So just like we did over here, remember you're going to solve the expression on the left, solve the expression or simplify the expression on the left, simplify the expression on the right, and make sure that they come out to be the same answer. So 6 times 3 is 18. When I take 1 away, I get 17. The 17 doesn't really get any simpler than that, and sure enough, those are equal to each other. In this next example, my goal is again to isolate the k, get it all alone. It's got both addition and multiplication in the way. So I can get rid of this added 13 by subtracting 13 on both sides. That will leave me with just my 4 k's on the right. Over here on the left, a 7 minus a 13 is going to give me a negative 6. Then to get rid of the 4, since the 4 is being multiplied by k, I'm going to divide by 4 on both sides of the equation. The 4's will go away on the right side, leaving me with just a k. On the left side, negative 6 divided by 4 can be reduced to a negative 3/2. I'm hoping by this stage that you're able to see why we might actually want to have this algebraic process, because I think you would have to guess values of k for a really long time before you would get to negative 3/2 just by guessing. So hopefully, even though we're only 10 minutes into our first day of algebra, you're already starting to see the wisdom of these two rules and why we do the math this way instead of just by guessing what the answer should be. We do still need to check this answer, so I'm going to take this negative 3/2 and put it in place of my k. That's going to give me 7 on the left, 4 times a negative 3/2 on the right, plus 13. So following the order of operations, I need to do the multiplication first. I'll make that into a fraction and reduce it. So I end up with 2 times a negative 3. That's going to give me negative 6. And when I add 13, I get 7. The left side stays a 7. And since those answers are the same, that means that this answer is the correct solution for the problem, because when I used it to evaluate my expression, it came out to be 7 on both sides.